Hello, welcome back everybody to Learning as a Hobby. In this video, I want to continue on my studies. In this video, I'm going to do the summary for section 1.3 and 1.4 in John Taylor's Classical Mechanics. So let me bring up the notes and we'll go through the summary. Okay, in the last section, 1.1, 1.2, we went over time and space, and now he wants to go over mass and force. So that's what section 1.3 is about. So we'll start with mass. All right, so here is the definition. Let me just move the screen out of the way here for a second. Okay. Mass characterizes an object's inertia, and by inertia, we mean an object's resistance to being accelerated. Right, and to make it quantitative, we have to have units of mass and ways to measure an object's mass. So the unit of mass that is internationally agreed upon is the kilogram, and the kilogram is defined in terms of the mass of a specific chunk of platinum iridium that is stored at the International Bureau of Weights and Measures outside Paris. So that's what it's defined in terms of. It's not like an intrinsic measure or something, or like some kind of natural measure. It's just a chosen object that has a specific mass that we choose to use as our unit. So that's what the definition of the kilogram is. Right, and we also have to have a way of being able to measure any object's mass, again, just so that we can make it a quantitative concept. And one way, this is sort of like a theoretical way of doing it, which is not actually practical in the real world, but we can define something called an inertial balance, which compares masses of two objects in terms of resistance to acceleration. So what you have is, let me grab my pen here. So what you have is a thin rod over here that connects the two masses. So say this mass, we know the mass M2, and we want to see whether mass 1 is larger or smaller than mass 2. Then we can connect them with that rod, and then what you do is you attach a string to the middle of the rod, and you apply a force to the string. So you pull it away, and if one object has larger mass than another, then, for example, if M2 has larger mass than M1, then there will be, then the rod will rotate. So it'll rotate like this because the mass 2 resists acceleration more than the mass M1. Right, so, or if they have the equivalent mass, then when you pull the string, there won't be any rotation at all. So this is what he defines to be an inertial balance. So we can use this to compare different masses together, their relative masses. All right, so if M1, here on the side, I'm just saying what I just said, M2 greater than M1, then M2 is accelerated less, and the rod will rotate when a force is applied to the string. Right, so that's called an inertial balance. Another more practical way of measuring an object's mass is by measuring their weight, and that's because the weight of an object is exactly proportional to the object's mass. So here, the weight is equal to the mass of the object times this constant, which is due to gravity. This number is constant as long as you stay close to, you have two objects in the same region, so they're accelerated by gravity in the same, but to the same extent. So, for example, two objects near the surface of the Earth, the acceleration due to gravity there is, if I remember correctly, it's approximately 9.8 meters per second squared. It's something like that. So because of that fact, we can measure the mass of two objects, but of an object by just weighing it. So for example, here you have a gravitational balance, And here you have your unknown mass. You put it on one side, and you keep adding known masses to the left-hand side until the thing is balanced, right? And then once the gravitational balance is balanced, then you just look at how much mass you have here, and that's how much mass is over here, right? So that is a more practical way of measuring masses. So same mass if and only if the two objects have the same weight. Right next, he talks about force. So he starts with an informal definition of force, which we have sort of like an intuitive feeling for, especially when we're the ones exerting the force. So, if you're like lifting a dumbbell or something, you know that you're applying a force, right? So informally, you can think of a force as any type of push or pull, but it doesn't have to be you imparting the force. There's a force can be imparted by one inanimate object at another. For example, the earth accelerates a rock towards the center if it falls off a cliff or something, right? One of the most important skills for the student of elementary mechanics, he says, is to examine an object's environment and be able to identify all the forces on the object. All right, so that's I guess something that we're going to have to practice. Again, we need to know about units. So the unit of force that is agreed upon is the Newton, which is the units are written as N, so the N stands for Newton, and it's defined to be the magnitude of any single force that accelerates a standard 1 kilogram mass with an acceleration of 1 meter per second squared. So in other words, 1 Newton is 1 kilogram meter per second squared, right? And then he gives two formal definitions, or I guess more formal. I don't know if there are other definitions of forces. There may be. Like I said, I'm not. I'm this is all new stuff to me. I don't know anything about physics yet. So, but anyway, he gives two definitions. The first one is a given force is said to be m newtons if by itself it accelerates a standard kilogram with an acceleration of m meters per second squared, which the definition there is, in other words, is given in terms of Newton's second law, which we'll get to in a minute. But he says number two is there are philosophical reasons why you would prefer one definition over the other. And let me go over number two first before I say what he says about that. So the other way you can define uh, a force is in terms of, for example, using a spring balance. So here, if you calibrate the spring, or let me get my pen, calibrate the spring down here to measure exactly 1 Newton on the scale. So you have like a pointer here, and exactly 1 Newton force is exerted here, so that the dial reads 1 Newton here. And then you have another spring attached to a balance arm. So here's the balance arm. And you have a pivot, let's say like it's a movable pivot, and the ratio of the two lever arms here allows you to measure any other multiple or fraction of a Newton on the other dial. So for example, if the ratio is in ratio 2 to 1, then the force that you'd have to apply over here, F2, would have to be 2 Newtons in order to keep the scale balanced, or in order to keep the spring balanced. Or I don't know, what is it called? Spring balance. In order, you know what I mean. In order to keep this thing level, right? And if you move the pivot so that the ratio of the lever arms here change, then that will have the force that you have to apply to the second spring here will change, accordingly. So you can measure any force using this spring balance device. Right, so defining a force that way, he says, is maybe philosophically a bit better, because the second definition separates the definition of force from the experimental nature of Newton's second law. So in other words, there could be confusion, I guess, from the first definition about whether Newton's law follows just directly from the definition of a force, or whether it's an experimental thing, right? If it's verified experimentally, whereas if you use the second definition, then Newton's second law is an experimental fact. All right. And here I just, saying what I just said above, adjusting the lever arm ratio, we can calibrate the spring balance to have two reads any desired force, right? Forces are vectors, so they, in addition to magnitudes, they also have directions. So he also defines what we mean by the direction of a force, and the definition he gives, it's the direction of the resulting acceleration on the object. So, if the force, if you apply a force to an object and it accelerates it in a certain direction, then we define that to be the direction of the force. Right. So again, forces are vectors, so you have magnitudes and directions. Okay, then we get to Newton's first and second laws. The first law is called the Law of Inertia, and it states, in the absence of forces, a particle moves with constant velocity. And this first law follows from the second law, which we'll talk about in a second, with a subtle caveat that he talks about later on in this section when we get to inertial frames. Right, the second law is for any particle of mass m, the net force F on the particle is always equal to the mass times the particle's acceleration. So in other words, F equals ma, which I have written down here. So this part is the vector sum of all the forces on the object. Right, so in other words, it's the net sum of the forces, and a is the acceleration of the object. So in other words, that's the first derivative of velocity with respect to time, or it's the second time derivative of position. Right, and just as we mentioned above, spring balance definition of force implies that the second law is experimentally verifiable. Okay. So we're going to assume that, well, let me read the definition first. So a point mass, or a particle, for example, has mass. So this is sort of like a theoretical fiction. It's, something that makes thinking about things easier and writing formulas down easier. So a point mass has mass but no size, can move through space but has no internal degrees of freedom, has translational kinetic energy but no energy of rotation or of internal vibrations or deformations. All right, so in this chapter, Newton's laws were only going to be considered as being applied to a point mass. We'll look at how the laws apply to extended bodies later on in the book. I think he says like chapter 9 or something. But right now you can think of like an extended body as a collection of point masses, and the reason that we want to do this in terms of point masses first is because point masses are simple. Sorry, that's my phone. Let me just turn the volume off for a second. What was I saying? Because we want to do things in terms of point masses because they're simpler than extended bodies. So it's easy, just as we're getting used to these things, it's easier to work with point masses. Okay, here's a definition because we're going to make a second statement of Newton's second law in terms of momentum. So a particle's momentum p is defined in this way. So the momentum is equal to mass times velocity. And in classical mechanics, it's taken for granted that the mass is constant, which I guess is not true in relativity theory. So in classical mechanics, that means that the time derivative of momentum is equal to the mass times the time derivative of velocity, or in other words, that's the same thing as mass times acceleration, which is the force. So if you take the time derivative of momentum, you get the force. Okay, so we can actually rephrase Newton's second law like this. So the force is equal to the first time derivative of momentum. And he does make a note here: F equals ma, and F equals the time derivative of momentum are not equivalent in relativity theory. However, with F and P suitably defined, that F equals, the derivative of P with respect to time is still valid in relativity, right? So obviously we're not going to look at relativity now. I think he has a chapter on special relativity later on in the book. I think it's like chapter 15 or something. So it's not really going to be an issue for us right now. Right, he does have a little bit of a paragraph or so on differential equations. And one of the reasons that I decided to start a series on differential equations is because you need to know how to solve differential equations for classical mechanics. So here he says almost all laws of physics are or can be cast as differential equations. So you're going to need to know how to model with differential equations, and you're going to need to know how to solve differential equations, right? And in particular, for example, Newton's second law is a differential equation, right? F equals m times the second time derivative of position. So it involves the derivative of a position. Therefore, it's a differential equation. All right. And he does like a simple example, but I think there's a couple examples in the exercise set for this section where he asks you to solve very simple differential equations. So we'll do those when we get to the exercises. Okay, and the last thing he talks about is inertial frames. So for example, the reason we need to know about this is that Newton's laws cannot be true in all conceivable reference frames. He gives some examples of situations where that doesn't happen. And here's the definition: an inertial reference frame is a reference frame in which Newton's first law holds. And if the law of inertia, which is Newton's first law, does not hold, then we say that the reference frame is non-inertial. And this should be underlined here. Right, so a reference frame is inertial if it's non-accelerating and non-rotating. And you can identify whether a reference frame is inertial by seeing if the law of inertia holds, and that implies that the second law is an experimental fact. So what was I going to say? Oh, he gives a way of visualizing this with an example of, for example, if you have a moving train that is moving along a straight track that at a constant velocity, then we would consider like if you put an ice cube, for example, on the floor, that ice cube with respect to the train can be considered as having no forces acting on it. Therefore, it's moving at a constant velocity. In fact, with respect to the train, it's not moving at all. So it's, the constant velocity that's moving at is zero. But if you are on so that's an example of an inertial reference frame. However, if you're on another train that is moving at constant velocity with respect to the or if you're standing on if you're standing outside the train and watching it in the distance go by, the train is moving at a constant velocity on a straight track. So if you were able to see through the side of the train car and see the ice cube, it would be moving at a constant velocity. So again, that would be an example of another inertial reference frame. So both of those reference frames are inertial. However, if you're on another train that was accelerating with respect to the other train, then that reference frame would not be inertial because, for example, if they were moving in opposite directions, let's say, then the one train is moving with a constant velocity going this way on a straight track, and the other train is moving this way, but it's accelerating. So let's say it's going faster as time goes on. So it's getting faster and faster, non-zero acceleration. Then if the person on the other train were able to see the ice cube on the floor of the other train, then the ice cube would no longer appear to be moving at constant velocity. It would be moving it would be actually accelerating in the opposite direction. So that would be even though there's no forces being exerted on the ice cube, that would mean that that moving train, the accelerating train, is a non-inertial reference frame. So that's like one of the intuitive examples that he gives, just to help you visualize what all this is saying. I found that to be a good example. It helped me wrap my head around it. So okay, so We'll explore how the laws of motion change in non-inertial reference frames later on, he says in chapter 9. So we won't worry about non-inertial frames until then. So for now, we'll confine our attention to inertial reference frames. Okay, and then lastly, he gives like a definition, I guess, of what we would consider a classical model of nature or physical model of nature. Um, it's a model of nature in which the first and second laws hold precisely and universally, right? This is not something that holds true, for example, in quantum mechanics or in um, relativity. So uh, classical mechanics, at least according to Taylor, is completely represented by models that follow this rule here. All right, so that's basically section 1.3 and 1.4. There's only I think there's like only three or four problems for these two sections. So I might even be able to get them done today and then post them later on today, if I have the time. But if not, then definitely by tomorrow. And then we can move on to finish up section 1B in Axler's linear algebra done right. All right, so let me stop the screen share, and so I'll see you guys in the next video, which will be the exercises for this section. Until then, keep learning. I hope you guys are enjoying the videos and you're learning something. And again, don't forget to like and subscribe because it helps the channel grow and tells YouTube to share the videos with other like-minded people. Again, I'll see you guys in the next video.